In this section, we will consider limits of functions at infinity. We will find that limits of functions at infinity have similarities to limits of sequences, especially in the case when sequences are given by explicit formulas. We will look at the definitions of the limits of functions at positive and negative infinities, and we will consider a number of examples to evaluate limits of infinity. To help us with this task, the concept of 1 divided by large gives small will prove very useful. We used that concept already when evaluating limits of sequences. It turns out that this concept is also very useful to evaluate limits of functions at infinity. Exponential functions are particularly useful in life sciences. We will use the new language of limits at infinity to highlight properties of exponentials. And one additional topic that we'll look into is going to be the infinite limits at infinity, which is a very, very special case when function takes on arbitrarily large values as the variable goes to positive or negative infinity. So to start, let us consider a motivating example. In 1930s and 1940s, French biologist Jacques Monod was looking at rate of bacteria growth as a function of nutrient. It is natural to assume that if the nutrient is scarce, then the bacteria growth will be slowed down. They will not reproduce as fast as if when the nutrient is abundant. However, another thing is that if you start to add more and more and more nutrient, the bacterial growth factor will not grow unboundedly. In fact, there is a certain saturation level, and it doesn't matter how much nutrient is in the environment, the bacteria just cannot bypass that level. It seems like that level is dictated by biology. So Jacques Monod collected some data and he fitted the following function into the data. That function is known as the Monod growth function. It turns out that the same function was introduced in biochemistry under the name of Michaelis-Menten function, and in biochemistry, that function modeled enzyme reactions. Let us consider the Monod function in slightly more detail. Here we have a plot that was produced in Desmos. You can see the table of values corresponding to all these points on the graph, and you see the graph that connects those points. If we look at those values, what we observe, those values start at 1.3 for n equals 5, but for n 100, we have 1.904. For 500, we have 0.9801. For 1,000, we have 0.99004. For 10,000, we have 1.9990065. So there's something that we notice in these values. They start to approach 2, a value of 2, which is right over here. So there's this value of 2, and we see that the function gets closer and closer to the value 2 as the amount of nutrient N increases. That is a reflection of the fact of biology, something about the bacteria biology that only allows bacteria to reproduce with a certain rate, and that rate cannot be surpassed no matter how rich the environment in nutrient. At the same time, we realize that if we look at that function, we realize that we can get as close as possible to the value of 2 by making values of the variable n sufficiently large. We would like to distinguish that behavior when function approaches a particular value when the variable gets larger and larger and larger. And to distinguish this behavior, we will introduce the concept of limit at infinity. So here's the definition. Suppose we have a function that's defined on some interval that includes infinity. We say that value L is the limit of function f of x as x approaches infinity, and we will write this formula, which I'll go over in a second, if values of the function can be made arbitrarily close to value L by taking x sufficiently large. So let's take a look at this example one more time. So the value 2 is the limiting value. And we can think about certain distance from that value. And we realize that in the beginning, the values of the function are not close enough to the limiting value. But starting from some value of n, in this case it looks like 20, the values of the function will be contained within that bound. Now we can think of a smaller bound, and we notice that now we have to wait a little bit longer before values of the function will be inside the bound. Nevertheless, it is possible to tell, starting from this location, all of the values of function will be within that bound. As a matter of fact, no matter how close we will put that bound to the limiting value of 2, there will be a spot on the n-axis, there will be that spot, such that after that spot, the function is within the bound. This is what it means by taking x sufficiently large. By taking it sufficiently large, you guarantee that function is close to the limiting value. It's actually more than that. It means that starting at a certain point, the function stays close to that value. If it does, then we have limits at infinity. Let me go over the notations a little bit. So in particular, the limit, the word limit, indicates that we consider limit of the function. L is the value of the limit. The x goes to infinity, we read as x approaches infinity, and indicates the type of the limit that we're considering. Well, f is the function in question, right? And altogether, it means that values of the function can be made arbitrarily close to L by considering sufficiently large values of the variable. There's another notation that is often used in the literature for the limits at infinity, and it reads as follows. The first portion says f of x approaches L, and that last portion reads x approaches infinity. And if you read it all together, you will have f of x approaches L as x approaches infinity. Let us consider a few examples of functions that have limits at infinity, as identified by the graphs on the slide. So first of all, we will note that infinity is not really a number. And the meaning of it is that with numbers, you can add them together, you can subtract them, you can divide one by another, or you can multiply them. You cannot carry those operations easily with infinities. So maybe you can say infinity times infinity is infinity, but infinity minus infinity is an indeterminate form, and we don't really know what is the value of that. Instead, the fact that x approaches infinity means that x takes on larger and larger positive values. Think about x equals 100, x equals 1000, x equals 10,000, x equals 10 million, and 10 to the 8, and 10 to the 9, and so on. So x will be taking on larger and larger and larger values. So here's a few examples of the functions that have limits at infinity. So in particular, this first function has limit at infinity equals 1. We can see that as we go and increase values of the variable, values of the function are approaching 1. So we can say that in this case, the limit as x goes to infinity exists, and it is equal to 1. That function also has a limit equals 1. Here we go. You can see that it's approaching it. And this function also has a limit. Apparently, in this case, limit is equal to 2. So let me write it down. As x goes to infinity equals 2. And notice that the function oscillates while getting closer and closer to y equals 2. In a very similar fashion, one can define the limit as x approaches negative infinity. In this case, we will be considering what happens to function when x takes on sufficiently large negative values. Therefore, we can say that limit as x approaches negative infinity of function f of x is equal to 1. The definition is very similar to the previous one. We say that capital L is a limit of function f as x approaches negative infinity if values of the function can be made arbitrarily close to value L by taking x sufficiently large negative. It turns out that it is possible to do arithmetic on limits. In particular, if limit of function f exists and limit of function g exists as x goes to infinity, then limit of the sum exists and equal to the sum of the limits. Also, limit of the difference will exist and it will equal to the difference of the limits. The limit of the product will exist and it will be equal to product of the limits. And limit of the fraction will exist and will be equal to the fraction of the limits, assuming that the denominator is not 0. The similar statements hold for limits when x goes to negative infinity. Limit laws are very useful for evaluating limits in practice. In the following, we will consider a few examples where we will use limit laws to evaluate limit, and we also will use other reasoning. So let's start with the simple example where we don't really need limit laws just yet. We will just consider other reasoning. What is the limit as x approaches infinity of 1 over x? It is sufficient to think of 1 being divided by a large positive number. When 1 is divided by a large positive number, the result is a small positive number. As x is increasing and gets larger and larger and larger, the division by x gives the result that's smaller and smaller and smaller. Sending that process all the way to the limit, we conclude that the limit is 0. If we would like to see a different confirmation for that fact, we can look at the graph. We know that the graph of the function y equals 1 over x will approach the x-axis as x goes to infinity. And that's another way to convince ourselves that the limit of 1 over x is 0. You can make that statement mathematically precise, but it's probably a little too much for the sake of this class. Let us consider our next example. Limit as x is approaching infinity of 1 over x raised to n. And n is positive in this case, which is important. If n is positive, x raised to n is growing larger. when x approaches infinity. So again, we have the situation of 1 over large number, and we conclude that the limit is 0 because as x to the n gets larger, the result gets smaller, and in the limit, the result is 0. Our next example is slightly different. X is now approaching infinity, and the fraction that we're looking at is 1 over 1 minus x. Again, there are many different ways to approach this problem, and you can make it mathematically precise. However, for the purpose of this class, the following will be sufficient. We notice that x is getting larger, getting large positive. Well, minus x is correspondingly getting large negative. At the same time, 1 minus x is also getting large negative. Why is this so? Because 1 will not matter. We'll be subtracting a very large number, like a 10,000 or a million. This 1 will not make an impact. 1 minus x will be a large negative number. So what we're looking at is 1 over large negative number, which gives us a small negative number. Now, what we'll be looking at a value that is approaching the 0, but approaching it from the negative side, from below. Nevertheless, as we send that process into limit, in the limit, that number will be very, very small, and it will approach 0. It will be negative, but it will be approaching 0. Since the value of the function can be made as close to 0 as possible, we conclude that the limit is 0. Our next example is look at the monad function and look at the limit as n approaches infinity of the function Rn. So let me copy it as n approaches infinity of 2n divided by 5 plus n. So in this case, it's hard to jump to a conclusion. If we look at that expression, we realize that we have large number over another large number. And it's an indeterminate form, and it's not clear which value this will be equal to. Another way to write large over large is to put infinity over infinity. So you will see me writing that many times just to get the intuition. So if we have an indeterminate form, our goal is to rewrite the expression so it becomes determinate. A typical trick is to divide by a power of n. In this case, dividing by n could be appropriate. So let us give it a try. So what we're going to do, we're going to take the 2n and we'll divide it by n. And we will take 5 plus n and we will also divide it by n. Another way to write that division is as follows. You can have 2n divided by n. That's the first fraction. And another one is 5 plus n divided by n. Two different ways of writing the same thing. You can use your favorite. Once I've written it that way, I can simplify. In the numerator, we can just have 2. In the denominator, I will break the fraction into 2. I'll write 5 over n plus n over n. And my last simplification would be to replace n over n with 1. In the numerator, I'll have 2. In the denominator, I'll have 5 over n plus 1. So at that point, we'll start to use limit laws. We're actually very ready to make a conclusion, and to make the conclusion mathematically solid, we will use limit laws. So in particular, A limit of a fraction is a fraction of the limit, so I will replace limit of a fraction with limit as n goes to infinity of 2 divided by limit as n goes to infinity of 5 over n plus 1. All right, we're pretty much done in the numerator. However, we can do another application of a limit law in the denominator. In the numerator, I will put limit as n goes to infinity of 2, and I don't need to do anything at the moment. But in the denominator, limit of a sum is replaced with the sum of the limits. We are ready to make a conclusion. So limit of 2, we know what this is. It is 2, because 2 is independent of n. As n goes to infinity, 2 stays the same, its limit stays the same. Absolutely the same way, limit of 1 stays 1. However, limit of 5 over n, it's 5 over a large number, that limit is equal to 0. So we have 2 divided by 0 plus 1. The result is 2, and that is the number that we saw the values of the function we are approaching. So here we go, we observed it numerically, and we confirmed it by doing evaluation of the limit. Let us look at another example. Limit as x approaches infinity of x squared divided by 5 minus x cubed. Again, we have an expression in the form large number over large, and that means that this expression is indeterminate, and we need to rewrite it to make it determinate. A typical trick of choice is dividing by a power of x. We have two powers that jump at us, like x squared and x cubed, and as a matter of fact, both can be used. I will go with x cubed. So I divide by x cubed in both numerator and denominator. Here goes. Limit as x approaching infinity. In the numerator, I will take x squared and divide it by x cubed. In the denominator, I'll take 5 minus x cubed, and I divide it by x cubed. Okay, let me simplify the expressions a little bit. In the numerator, I will have 1 over x. In the denominator, I'll split the fraction. I will have 5 divided by x cubed minus x cubed divided by x cubed. Let me rewrite the expression one last time before I apply limit laws. As x goes to infinity, we have the following fraction. In the numerator, we'll have 1 over x. In the denominator, we'll have 5 over x cubed minus 1. Now we use limit laws. So in particular, limit of a fraction is equal to a fraction of the limits. So I'll have limit as x goes to infinity of 1 over x. That's the numerator. And then I have limit as x goes to infinity of the following difference. 5 over x cubed minus 1. Okay, one more step. I will copy the numerator as x goes to infinity, limit of 1 over x. And in the denominator, limit of a difference is difference of the limits. So it's going to be limit as x goes to infinity of 5 over x cubed minus limit as x goes to infinity of 1. We are ready to make the final computation. So limit of 1 over x, we know what that is. It's 1 over a large number. That limit is equal to 0. Limit of 5 over x cubed, we know what that is. It's 5 divided by a large number. That limit is also 0. And limit of 1, as x goes to infinity, 1 doesn't change. It stays the same, so limit of 1 is itself. So evaluating limits, we have 0 divided by 0 minus 1, altogether 0. So the answer to this problem is 0. Before we move to the next example, let me notice that I show all of this intermediate step to highlight the fact that every time we make a mathematical step, we use a theorem, a statement, a formula behind it. In the beginning, I prefer that we go very carefully and identify every result that we use. After we've done it a few times, it is reasonable to speed up, to accelerate. In particular, we could have jumped to the answer right from here. So we could say, wait a second, that goes to 0, that goes to 0, and that stays 1. Overall, you have 0 over 0 minus 1 altogether equals 0. We could have done that, but we wouldn't highlight the fact that we had to use limit lows. But as we get more confident, we are allowed to make some shortcuts. Our next example is limit as x goes to infinity of the following expression. We have square root of x squared plus 2x minus x. So if we think about it, as x goes to infinity, x squared plus 2x gets large. Square root is an increasing function. It is also get large. So we have a large number in the first term. And x is also get large. So overall, our expression has the following format: large minus large. Large minus large is an indeterminate form. It is impossible to make a conclusion what the value will be unless we do additional analysis. So what we're going to do, we're going to have to rewrite that expression so it becomes determinate. When thinking about the next step, we look at this expression and we ask ourselves, what part of this expression we don't like the most? Because the part that you don't like the most is a good first step to address. And the part that I don't like the most here is the square root. How do we address square roots? We address square roots by multiplying them by their conjugates. So here we go. We can think of this as a fraction of that entire expression divided by 1. And what we're going to do next, we're going to take that expression. So here we go. So it's going to be square root of x squared plus 2x minus x divided by 1. And we will multiply both numerator and denominator by the conjugate. In that case, it would be square root of x squared plus 2x plus x. We'll put it in the numerator. We'll put it in the denominator. And then we work out the expressions. Now, the way the conjugates work is that if you start with a minus b and multiply by a plus b, the result is a squared minus b squared. So that is the formula that we use in the numerator. Using the formula in the numerator, we realize that we will have square root of x squared plus 2x everything squared minus x squared. And in the denominator, we will have square root of x squared plus 2x plus x. There is additional simplification in the numerator. In particular, the square and the square root cancel out, and we will have x squared plus 2x minus x squared. And then x squared cancel out, and we'll just have 2x. So let me write it over here. It's going to be limit as x goes to infinity of 2x in the numerator. And in the denominator, we'll have x squared plus 2x, everything plus x. So did we improve the expression? Well, large minus large is done. If we look at the denominator, now we have large plus large, and that is also equal to large. So that indeterminacy is gone. It is now determined. Here we didn't know what it is. Here we do know. It's a large number, large positive number, if you want. And in the numerator, we also have large positive. So now we have indeterminacy large over large. And on one hand, it's bad because we still don't know the answer. On the other hand, that we saw just in the previous example. And the solution was to divide by a power of x. So we can try that solution here as well. We will divide by a power of x, and there are different powers that jump at us. I think we can start by dividing by x. So here we go. limit as x goes to infinity, we will take 2x and we divide by x, that's 1. And then we will take square root of x squared plus 2x plus x, and we divide everything by x. Okay, so let me work out the expressions. In the numerator, simplification is straightforward. The numerator simplifies to 2. Denominator is a little bit trickier, so let me work it out separate. So let me start from square root x squared plus 2x plus x divided by x. Let me start from breaking the fraction into 2, so I'll have x squared plus 2x divided by x plus x divided by x. Now, the second term is easy. It just cancels out to 1. But the first term is a little tricky. So what we're going to do, we're going to use the following fact. If x is positive, x is equal to square root of x squared. The interesting part that I made it specific, I said if x is positive. And that's an indication that if x is negative, the answer will be different. And in fact it is. If x is negative, then x is equal to negative root of x squared. And then you ask, why is this so? Well, the convention is that radical returns the positive root. From the two possible roots, radical returns the positive. If x is negative, we will have to explicitly add the minus to make radical to return the negative number. So, one more time, if x is positive, x can be replaced with radical of x squared, and if x is negative, x can be replaced with minus radical of x squared, and that's a technical trick that I want you to think about. We will use that later. So with that, I can take the first term, and I'll have square root of x squared plus 2x. And here I will put radical of x squared, because in our case, x is positive. The next thing that I want to use is that if we have radical a over radical b, that can be simplified to a radical of a fraction, a over b. Okay, there has to be 2 here. Let me combine these fractions. So I have radical of x squared plus 2x divided by x squared plus 1. Now, inside the root, I will break the fraction into 2. So I'll have x squared over x squared plus 2x over x squared plus 1. And finally, I will write radical of 1 plus 2 over x plus 1. So such a long expression, but now I can copy it into the denominator of the answer and continue. So let me put it here. 1 plus 2 over x plus 1. I have to shift it a little bit to the left, so bear with me. And now we are ready to make the conclusion. So in particular, as x goes to infinity, 2 stays the same, 1 stays the same, 2 over x will go to 0, and 1 stays the same. Overall, using the limit laws and, as a matter of fact, property that square root is a continuous function, we conclude that the answer is 2 square root 1 plus 0 plus 1. After simplification, we have 2 over 1 plus 1 equals 2 over 2 equals 1. So as a matter of fact, limit of that expression is equal to 1. Let us consider an additional example. Limit as x approaches infinity of cosine x. We can take a look at the graph of cosine, And we notice that cosine is a periodic function, and it is repeating itself again and again and again, all the way to infinity. As a result, we realize that y equals cosine x does not approach a particular value as x gets larger. Well, it approaches some values. We can get any value between -1 and 1. However, there will be no value such that cosine stays close to it as x gets larger. Now, in this case, we conclude that there is no limit, and we'll write here limit does not exist. When we study graphs, we'll look for features of the graphs that are easy to explain, that look similar to us, they're easy to identify. So if you look at the graph of the function over here on the plot, you will notice that that graph follows a line. When a graph follows a line, we call this line an asymptote. So in particular here, the graph follows a horizontal line. So we have two horizontal asymptotes, one at y equals 1 and another one at y equals -1. So horizontal asymptotes are connected to limits at infinity. In particular, you can see that as the graph follows a line, it is approaching the value, in this particular case, value of 1, as x goes to positive infinity, value of x is approaching 1. And that also indicates that the graph will stay along that value. And when the graph stays along that value, it follows a horizontal line. So that line should be an asymptote. So if we have a limit at infinity, we also have a horizontal asymptote. Absolutely the same way, if we have limit at negative infinity, like for example here, x goes to negative infinity, there is a limit, -1. In that case, we also have a horizontal asymptote. The graph has to stay close to that value, and as it stays close to the value, it follows a horizontal line. So therefore, oftentimes we will see definitions introduced. If limit exists at plus infinity or minus infinity, then we have a horizontal asymptote. And the horizontal asymptote is given by the equation y equals L, where L is the value of the limit. Let us try to apply that definition to an example. We will look at that function, we will establish a limit and confirm that we indeed have an asymptote. So the graph suggests that we should look at two limits, limit at plus infinity and limit at minus infinity. So let's start with limit at plus infinity first. Let's take a look at the limit of x squared plus 1 under the root over. As we look at this expression, we realize that we have an expression in the form large over large. And our favorite approach is to divide by a power of x. In this particular case, you can try to go ahead and divide by power of x in both numerator and denominator. Now, it turns out that in this case, we don't really have to introduce additional division because our expression is so simple. We can work with that expression directly. So what are we going to do? We're going to copy the x goes to infinity. We're going to copy the numerator, x squared plus 1. And what we will do, we will replace x with square root of x squared. Notice that when x is positive, that's a correct statement to make. So here I will put square root of x squared. Then we can go ahead and combine the square roots into the square root of a fraction. And then we break the fraction into 2. So it's going to be x squared over x squared plus 1 over x squared. And finally, we will simplify and we will be ready to evaluate the limit. So we'll have x squared cancels x squared. We have 1 plus fraction 1 over x squared. Okay, we are ready to conclude the value. When x goes to infinity, we know that 1 over x squared will go to 0. Therefore, we are looking at 1 plus 0 equals 1. Since limit as x goes to infinity of square root x plus 1 over x exists, we conclude that y equals 1 is a horizontal asymptote. Let us now consider the other case, limit when x approaches negative infinity of square root of x squared plus 1 divided by x. In a similar fashion, we can replace x with negative square root of x squared. Why is this negative? Now we are looking at the case of x less than 0. And when x less than 0, this is again a correct statement. We have x squared, which is a positive number. We'll take radical of x squared, which by convention returns a positive number, and adding a negative on top of it will make the result negative. Negative on the right, negative on the left makes a correct statement. So, but that negative will introduce a difference. In the numerator, we will still have square root of x squared plus 1. In the denominator, we'll have negative radical of x squared. And that negative can be brought up front, and we'll have a limit. Let me combine the square roots into square root of x plus 1 divided by x squared as x goes to minus infinity. We need to make sure that we keep that straight. And our last prep step is to simplify the fraction inside the square root. So we'll have x goes to minus infinity of the square root. So that fraction will be simplified to 1 plus 1 over x squared. Okay, so what can we tell? Now 1 over x squared will go to 0. X will take on a large negative number. X squared will take on even larger positive number. 1 over x squared will go to 0. So putting it all together, we will have negative radical 1 plus 0 equals negative 1. And that is exactly what we see on the plot. For x goes to plus infinity, the limit is 1. For x goes to minus infinity, the limit is negative 1. That's way too. Since limit as x goes to minus infinity of square root of x squared plus 1 divided by x is equal to negative 1 and the limit exists, we conclude that y equals negative 1 is a horizontal asymptote. Well, in fact, we'll have two asymptotes, y equals 1, and the function will follow y equals 1 when x goes to infinity, and negative 1 function will follow that asymptote when x goes to negative. Let us consider a special case, special situation, when function takes on large values as x is approaching infinity or negative infinity. We have four different possibilities. In the first possibility, x approaches infinity and the value of the function becomes large. In this case, we say that limit of f of x is equal infinity as x goes to positive infinity. Here's the situation. X goes to positive infinity, while the function increases. Here we have the case when limit of f of x as x approaches infinity is equal to infinity. Absolutely the same way, if value of the function approaches negative infinity, like for example here on this example, as x increases, value of the function also increases, maybe not as fast, but it increases and it continues to go down, and eventually it will approach negative infinity. So we say that in this case, limit of function f of x is negative infinity. Or we can look what happens as x is approaching negative infinity. If the value of the function becomes large, we have this case. If the value of the function becomes negative large, we have that case. So we will introduce this concept of infinite limit as a statement. As x is approaching infinity, value of the function also approaches the infinity. This is what we mean by infinite limit. Let us look at a few examples. So here's a simple one, x cubed, and we will look at two cases when x goes to infinity and x goes to minus infinity. For the sake of this course, it would be sufficient to recall the graph of x cubed, which is a cubic parabola. This is what it looks like. And we realize that as x approaches infinity, f of x equals x cubed gets on large values, large positive values. Therefore, limit as x goes to infinity of f x cubed is equal to infinity. On the other hand, as value of x approaches negative infinity, we notice that values of f of x equals x cubed get large negative. Here we go. The function starts to go down. The more we go to the negative infinity in the variable, as x is approaching negative infinity, we expect the function to take on large negative values. Therefore, we say that limit of x cubed as x goes to negative infinity is equal to negative infinity. Let us look at a couple additional examples. So let us start with this one. Let us consider limit as x is approaching infinity of x minus x squared. The expression is currently in indeterminate form. X takes on large values, x squared also takes on large values, and we subtract one large value from another large value. Therefore, it's indeterminate. Nevertheless, what we can do, we can rewrite an expression just a little bit to make it determinate. Here we go. Actually, the solution is very simple. All we have to do is to factor x out. We factor out x, and now we start to think. This gets large positive. 1 minus x, on the other hand, gets large negative. When we take large positive and we multiply by large negative, the result is definitely large, and it's negative. Therefore, we conclude that the value of that expression is approaching negative infinity. Let us take a look at the next example. So we have a limit of a fraction. In the numerator, we have x cubed plus x squared minus x plus 1. In the denominator, we have x squared minus 3. The question is, what is happening to this expression when x goes to plus infinity? In this case, again, we have large over large. And to understand what this limit is, we'll have to rewrite the expression in a determined form. In this case, we can use our favorite trick of dividing by a power of x. In particular, it seems informative to divide by x squared. Let's take a look. I will start by copying limit as x goes to infinity. And in the numerator, let me copy the entire numerator. I will divide by x squared. And let me make that denominator a little longer so we see that that's a mixed fraction over here. And in the denominator, I'll put x squared minus 3 divided by x squared. Well, let us simplify the expressions a little bit. We will break the fraction in the numerator into parts. And we'll have x cubed minus x squared plus x squared over x squared minus x divided by x squared plus 1 divided by x squared. In the denominator, we'll have x squared over x squared minus 3 divided by x. Let me rewrite the expression again. Limit as x approaches infinity of x cubed divided by x squared simplifies to x squared over x squared simplifies to 1, minus x divided by x squared simplifies to 1 over x, plus 1 over x squared, that's the numerator. And in the denominator, we'll have 1 minus 3 divided by x squared. So the analysis is almost complete. Let's take a look what we have. So in particular, we know that this expression will go to 0, and that expression will go to 0 too. Now, what I will have in the numerator, I will have a large number. I will have 1, and I will have a couple of zeros. So I'll have large plus 1 minus 0 and plus 0. Overall, when I take a large number, I add 1, I still get a large number, and I subtract 0 and another 0. The result is still large. Let's take a look at the denominator. Well, negative 3 over x squared, that's going to be a small number, and 1 stays the same. It looks like our fraction has the following form. Large over 1. When we take a large number divided over 1, the result is large. It is important that the signs are clear. So you can have large positive number, large negative number, and that's a big difference. But here, if we look carefully, we'll see that's large positive, and adding 1 and subtracting 0 will keep it large positive. So we have large positive number divided by 1, overall large positive number. Hence, we conclude that limit as x goes to infinity of that fraction, x cubed plus x squared minus x plus 1 divided by x squared minus 3 is equal to plus infinity. Let us consider one more example. We're looking at the limit of square root of x squared plus 2x minus x as x is approaching negative infinity. So let's take a look. As x goes to negative infinity, what can we tell about x squared plus 2x? Well, x goes to negative infinity. Well, let's take a look at the graph of x squared plus 2x. We can factor out x, and we'll have x multiplied by x plus 2. It's a parabola, opens up, and its roots are negative 2 and 0. Now, as x goes to negative infinity, which is this way, the values of the parabola are going up. So I conclude that as x goes to negative infinity, this expression goes to positive infinity. Square root of that expression also goes to positive infinity. Very good. So I will say that's a large positive number. Now let's take a look at x. X goes to negative infinity. That means it's a large negative number. Well, minus x, on the other hand, is a large positive number. So what do we have then? We have limit as x goes to negative infinity of square root of x squared plus 2x, that's one thing. And look, I will write it this way, plus negative x. So that minus over here I replace with plus of negative x. And I know that this is large positive, and negative x is also large positive. When I have large positive plus large positive, I get large positive. So my conclusion is that the limit is positive infinity. In conclusion, let us consider exponential functions and study their properties in terms of limits at infinity. Exponentials are very important for life sciences. They are used in many applications. Therefore, it is important to state their properties so that we can use them later. So we look at the graphs and we observe that in the case when the base is greater than 1, exponential function is monotonically increasing, and as the value of the variable increases, the function is growing unboundedly up. On the other hand, if we make the variable approach large negative numbers, we see that the exponential function returns values that are close to 0. Therefore, we conclude that limit at infinity of an exponential function is infinite, and limit at negative infinity of the exponential function is 0 when the base of the exponent is greater than 1. The opposite situation is in the case when the base is between 0 and 1. So it's strictly less than 1, but strictly greater than 0. In that case, as x approaching infinity, the exponential function goes to 0. So we have that limit. On the other hand, if we go to negative infinity, the exponential function becomes infinite. So limit at negative infinity will be equal to infinity in the case when the base is between 0 and 1. So the special case that's very important for us is the natural exponent, e. Natural exponent is strictly greater than 1. It's 2.73 and additional digits. So therefore, the exponential is equal to infinity at infinity, and the limit of the exponential at negative infinity is 0. Absolutely the same way, if we look at e to the negative x, which is the same as to say 1 over e raised to x, we notice that 1 over e is strictly less than 1. Therefore, we have a case of the exponent that is less than 1, and limit at positive infinity will be 0, and limit at negative infinity will be infinite. Let us apply the knowledge about exponentials to this particular example. A biologist, Gauss, conducted an experiment with parasitic organisms, and he studied how they grow in the population size. So in particular, his data was fed into the following function that is known under the name logistic function. And the function is given over here. And the claim is that this function fits the collected data and represents the population of the parasite after T days. So the question that we need to answer is to find the initial size of the population and the limited size of the population. The initial size of population is a fairly easy question. We just need to substitute the value of initial time, t equals 0. And according to this function, that initial value is 64 divided by 1 plus 31 multiplied by the exponential function raised to the exponent 0.7944 times 0. After simplification, we'll have 64 divided by 1 plus 31, which is 32. So 64 over 32 equals 2. That's the initial population. So we start with just 2 parasites. Very well. What is the limiting size of the population? The limiting size means that we monitor this population for a long time. So we are looking at values as time increases indefinitely. In other words, limiting size is given by limit of that function as t goes to positive infinity. All right, let's take a look at that limit. Limit as t goes to infinity of p of t. This is the same as to say t goes to infinity in the following fraction. 64 in the numerator, 1 plus 31 times e to raise to the power of 0.7944 t. Okay, according to the laws of limit, we can replace limit of that fraction with the following. The 64 will be here, 1 plus 31 will be here, but the limit can be pushed all the way onto that exponential. How do we evaluate limit of exponential raised to negative 0.07944 times t as t goes to infinity? Well, one way to think about it is to redefine the variable. So in particular, we can say, well, let's introduce y, which is equal 0.7944 times t. With that notation, that exponential can be replaced as e raised to negative y. Okay, so let us notice as t goes to infinity, y also goes to infinity. Because y is just a multiplication by 0.7944. When t goes on large numbers, y will become a large number. Therefore, it is safe to conclude that we are looking at limit as y goes to positive infinity. And we know what that limit is. When we're looking at exponential with the negative exponent, that limit is equal to 0. Therefore, we conclude that that limit is 0, and we are looking at 64 divided 1 plus 31 times 0, which is 64.